Perfect.
So welcome everyone. This is the Couples Biogeochemistry webinar for the Department of Energy's E3SM project. And we use this webinar to share some new results, both from people within the project and also people outside who are doing interesting things that are relevant to our activities, having to do with biogeochemistry in the land, ocean, atmosphere, and energy systems. So today our speaker is Anders Ahlström, who will be speaking about forestry and land use change and its impacts on land carbon storage. All right, so take it away, Anders.
Yep, thank you very much. I will present some results and some preliminary results and so on from some current work we're doing in Lund University in southern Sweden at the Department of Physical Geography and Ecosystem Science. Let's see now, my slide doesn't work. Okay, so I will basically actually start with a failed attempt to estimate land use impacts globally over 8,000 years. And basically what I learned from that, it's work I've been doing over the last couple of years, and then that this has guided some of the more recent work I started. I started a new position in Lund for like a year ago, and now I have some more students and so on. So we started these more long-term projects that I will also present towards the end. But I'm going to start with this kind of failed attempt using, in part, our model. That's the Lund Potsdam Jena LPJ General Ecosystem Simulator, LPJ GES. But we are not fully using this model. I will sort of try to explain what I did. So basically, the first work, or sort of the work here in total, is guided by the traceability framework, which many of you may know. Yichi Law, he's in Northern Arizona University. He was before in Oklahoma University. So we've been working together for a couple of years here on this kind of traceability framework. And what it does, it basically takes your model pool structure and represents it only as flows between pools and sort of turnover rates and partitioning coefficients, basically where the carbon goes from one pool to another. So basically building up this simple pool network in a single equation. And but what it basically shows is that all models, so far, all models that I know of are basically working the same way. They're dominated by first order kinetics, and they have basically the same pool change structure. So basically a change in a pool is the difference between the influx of carbon to the pool and the turnover rate that is then multiplied with the pool size. So I will sort of try to go through why this is relevant. So don't mind these equations too much. I will try to keep it more simple. So basically, right now, this is a transient version that came out a couple of years ago. And this is LPJ GES, our model. And this shows how this equation, which is, I don't know if you can see these green lines on top of the red ones. So basically, these green lines is for various pools from leaf, wood, roots, microbial, surface, metabolic, and whatnot, all these pools as simulated by the model, and in green is as represented by this equation, a very simple equation that we can run globally in a very short time. It's maybe just reading in and out the parameters. So it's not predictable. You also see to the right that it basically represents these pools and the change in time perfectly with only this equation. In a rather complex model, we have all kinds of tree mortality in LPJ GES. We have stochastic variations. We have competition between plants. And this doesn't matter. We can still represent it with this simple pool structure. So basically, this has led to one paper where we sort of assume that we replace parts of the model with what we call observations. They are, of course, not observations. They are global data sets of various processes. The most obvious ones are net primary productivity, which basically force the carbon cycle. So the carbon comes in, and the top of these carbon cycle architecture, and then it's transferred downstream to various pools into the soil and to the atmosphere and so on. So we can basically assume that nothing else changes, and we just exchange MPP. And then we sort of look at the global net carbon storage, or the global NEE or MBP, the net exchange of carbon, and we can see if we get a better model. And this is published. I'm not going to go into more in details. It came out late last year, and what we basically found is that the uncertainties between these various global carbon cycle data sets is larger than our model to those data sets. And that basically means that when we do exchange everything from, so we basically exchange turnover of vegetation, turnover of soil, and so on, and put that in the model. So we basically have a model that is completely adjusted by data. So it would benchmark perfectly against those global data sets. We still don't get a better model in comparison to a third or fourth independent data set. It's very difficult to find any robust benchmark to even see if we get a better model. So that's basically one of the backgrounds here, but I will not discuss it much more. So in this case, we are showing global, we're basically replacing MPP, and then we have the standard one in red, and we have the Global Carbon Project residual land sink, which is of course also not a perfect benchmark. I don't want to say that, but we have something that's independent, and we replace then the simulated MPP with these various GPP data sets from upscale flux towers and from MODIs, and it's rather hard to detect any real improvement, and the main characteristics of LPG gas do remain in those outputs. So the second thing that I've been trying is basically building on this, if this makes any sense, that we have this model pool structure where we simulate things, but we can also put data in it. So then I was thinking, why not build a model entirely of data? So instead of simulating anything really, I basically just build a simple pool structure. So we have vegetation, soil, and store soil, and we have harvested wood products. And then I try to populate these with data as well as I can, and I simplify it to a degree that I do have some kind of estimate. And then, so in this case, I was looking at land use change emissions over time. So to do that, I was thinking, I wanted to scale it over a long time. So I did use these various land use change reconstructions dating back maybe 8,000 to 10,000 years before present. And then I have these estimates of how land use have affected, for example, MPP, vegetation turnover, or soil turnover today. And then I scale this. I basically run the model from 8,000 years ago up until today. And I scale MPP and turnover rates with simulations now. So this is where the simulations come in. So there is some simulations here with LPGS, which is like a Holocene simulation, so that I do also capture changes in CO2 and temperature on MPP and turnover and soil respiration rates and so on. So these are all the data sets. I'm not going to describe them in detail. That sort of build up this model. So I'm using the best I could find a couple of years ago. Is basically optimization procedure, so that I do get at year 2000 or the year I have data, I do get that number perfectly. So it means that this model is also a perfect model today. So if we would benchmark it, it would be absolutely perfect present day. But if I change something, some parameter or some behavior of the model, it only changes basically back in time and into the future. But the present day behavior is always the same. So I hope this is clear. And I heard you said that no questions until after, but please, you feel free to ask me if there's anything right now. So in this case, you're looking at vegetation carbon, which is very simple. It's basically MPP times the turnover time of vegetation. And then I use these estimates of how land use have affected the turnover time of vegetation. And I basically scale that with time. And then I scale vegetation turnover with climate and so on as the model, as our offline DGVM predicts. And then I also scale MPP in time, so that basically MPP increases as our model predicts, and all of these. So it's not entirely data-driven, it's partly data-driven. And these data sets are, of course, very uncertain in themselves, but the model would at least reproduce them very well. So what we can do then is basically remove all land use impacts. So we have the actual vegetation as you saw in red. And then if I run the whole simulation again, without these reductions, I get the potential vegetation. Nitrogen deposition, we would have increased the nitrogen deposition through our activities. Human activities, we would still emit carbon dioxide, which benefits MPP in our model, and so on. And also warming, especially in northern hemisphere, the lengthening of the growing season and so on. We would see an increase in the potential vegetation carbon going up to somewhere close to 1,000 petagrams. And right now we are somewhere around 500 petagrams in above ground carbon, or vegetation carbon, I think this is. Including roots and not only above ground. And the difference here then, if we sort of say that the potential vegetation carbon is 0 and everything below that is a loss of carbon due to human activities, is shown in this figure. It's basically just flattening that blue line and setting it to 0 figure. And what it basically shows then is that in this case, with these simulations, it suggests that most of these carbons was lost before 1850, and then not as much, but still a significant fraction after 1850. There's also a green line there, something I sort of tried basically due to the turnover time that is optimized in this optimization procedure. I get a turnover rate of vegetation. Vegetation is of course, rather fast in comparison to soil. And the green line would be if we abandon all land use today, or at year 2000, how fast we will reach the potential vegetation carbon. And this is only first order kinetics. There's nothing, no consideration to land degradation or anything like that. It's purely mathematical how fast we would get back. And for vegetation, it's perhaps not that interesting. We can also then look at what has caused this. So basically, these are the losses just flipped around. So the losses in vegetation carbon over time. And the red is then a loss of mean residence time, and green is a loss in MPP. And I think the other legend to the left there is incorrect, I'm afraid. So, but it's the red and green text. So these are things I can do. And I also did it for soil. And this is where I hit problems that I was never able to overcome really. And what is sort of my point with this long introduction, rather technical introduction, is in a way this. So basically, the soil is much more complex and it's an underdetermined system. And I can optimize it the same way so that I get a perfect soil carbon pool sizes compared to any data set, global map I use today. But the problem is basically the distribution into multiple pools. So we could assume that the soil carbon is dominated by a slow carbon pool in size. Then we get a very slow system. We can also assume that it's dominated by a fast carbon pool, and then we get a rather fast acting system. And the difference between these two makes a very big difference on the impact of land use change and harvest on the carbon storage in the soil. And basically, these two models, I don't know if you can see that they look kind of different over the time, and it's also the green line there showing how fast we could sort of regain this carbon if we stop land use, maybe reforestation or some other method. Oh, sorry, there. So basically, these two models have an identical soil CH. I can give them any age I want that would match any radiocarbon I want, and they will still not be a constraint. They have identical year 2000 pool sizes, and they would benchmark perfectly in global benchmarks. And they even have identical mean residence times and turnover times. So I kind of abandoned this whole project after realizing this, that I don't have any constraints on the soil. And I also think it means that no other model can do this either. We do have some extra information from fluxes that I have not used here, but I don't know how good they are, to be honest. And it sort of means to me that more or less, of course, there's some common sense and some other experiments that can inform us on these things. But more or less, these global benchmarks cannot be used to constrain long-term behavior in a carbon cycle model, in no model. So in that way, most models are a guess. We can come up with almost any distribution into multiple pools and make them match better or worse with global benchmarks. And it still won't help us to constrain the future behavior of soil carbon. This is also true for our own model, LPG gas, then, that's also more or less some kind of estimate that's possible, but very difficult to prove. Oh, so basically I can still make a map. I just want to show you that this did result in a map. In this case, it's one realization, one possible sort of soil carbon model. Vegetation has its own sort of uncertainties from other estimations, I think. But the mathematical constraints of doing it is much smaller. It's not hard to. It does not have the problems that we can that we have with the soil carbon. So basically, in this case, this map would be 800 petagrams of carbon, and we could probably change this number around quite a lot. But the potentially, when doing an exercise like this, depending on what you put in it, is that the potential, at least losses of carbon, is high, but we can't, according, as far as I understand, at least my understanding is that we can still not constrain it. So it's very hard to come up with a number, and any model result is also just one of any basically estimate that's possible. So I've been trying to pick out some pieces here that I still think worked, and one of them is decaying carbon. So basically, these are the following slides here now, 2 examples of things I've been doing where I think that we can actually find some robustness, or where we can actually say what land use has done to the carbon cycle. Or like the third example is sort of an alternative method of perhaps how to address this that I started trying. So this one focuses on decaying carbon. So in an ecosystem, in a natural ecosystem that is not managed, that could be a dead tree. So the dead tree falls down, and eventually it's turned into soil carbon. And depending on the turnover rate of this decaying carbon, which is then the dead tree and everything that's sort of non-growing and is not in a stem that's supporting a live tree and so on. That's my definition of decaying carbon. It's very hard. This is a paper manuscript that's under review. It was hard to come up with a word for this. I started with dead carbon, but people didn't like that. So now it's sort of decaying carbon. So I was trying to explain. In a managed system, on the other hand, that the trees are harvested and they are removed, and they can be turned into furniture, to paper, or to bioenergy, firewood in some way. All of that is also decaying carbon in this kind of framework that I'm presenting. So and these 2 states basically are the alternative. So either the tree decomposes in the nature where it's turned after a while into soil carbon, or it's turned into some kind of product or used for bioenergy. And either of these have some kind of residence time or turnover time that determines how much carbon is in these two systems. So just a very quick one here. So basically, if we go back to these equations again, we can sort of rewrite them and so on and show that I don't want to focus on the equation. Let's just look at the last one. If you cool with the other equations, we can rewrite it and say the turnover time is the pool divided by the efflux of carbon, the carbon leaving the system. If you are in steady state, the flow into a pool is the same size as the flow out of a pool. And then you can use either input to the pool or output of the pool. We assume they're not in steady state. We need to use the output of the pool to determine turnover time. And if we just go back up here again, so basically to evaluate the impact of land use on a forestry system in this case, on the decaying carbon, but it would also be true for other land uses such as agriculture and so on. If we assume that the impact of management is not too large on the turnover rates in the soil, we could also include them. But otherwise, the only difference is the difference in turnover time. So basically, you harvest this tree, and if you leave it in nature, if it stays there on average for 100 years, you build up a pool that's 100 times the annual input of trees. If you take those trees and you remove them again and you make paper of them, the same amount of trees, and the paper only, let's say we burn it or something, let's say bioenergy instead, 1 year. That means that the pool in nature is 100 times larger if we leave it there, the amount of decaying carbon on land, than if we burn it. So in this case, with all of these simplifications, we only need to compare the turnover time in the natural ecosystem where the trees was harvested to the fate in the human management or in the harvested wood products, which also differ between products. So I basically tried to estimate this, and globally for every country, trying to estimate if their forestry has a positive or negative effect on decaying carbon. And so I basically start with soil carbon, and I have the soil efflux, which I've estimated. And if I divide the soil carbon from some data set, this is the WISE data set, and then the northern Arctic soil carbon data set too, that's been merged and then changed a little bit. But anyways, if I divide the soil carbon with the efflux, I get turnover time in the soil and litter in all pixels or grid cells on land. If I then have some other estimate of where forestry happens in a country, so basically we have a variability, spatial variability in soil carbon, so we need to know where the trees are harvested to come up with a sort of a country number on the potential sort of turnover time of decaying biomass in the ecosystem. So I have a map, so basically I weigh that. So for every country, I use these weights that represent harvest. I have a number of those that give me in the end an ensemble, but I'm only going to show you sort of the median numbers here. So then I can calculate a country number in the soil turnover time in ecosystems under forestry, where an ecosystem or sort of an ecosystem that has a larger share than another in the amount of forestry extractions, in biomass extractions, will have a larger weight on the country number than a one with smaller extractions do. So anyway, so it ranges maybe from around 10 years in the tropics up to more than 90 years when we go north. Or if, for example, for Algeria, where we have some of the harvesting up in the Atlas Mountains, I believe. It can also result, it's so small that the forest harvest in that country anyways. So it goes from maybe 10 to 90. And then I wanted to compare this to the turnover time of decaying biomass in human products or in anthropogenic products. And for that, I basically used outputs from this paper that was published a couple of years ago, where they used the FAO database of trade and end fates and a range of assumptions on what happens to this carbon if it ends up in landfills, if it's used for paper, if it's burned, and so on, and also where it's exported to. But that means I can track biomass, for example, burned in the UK, that comes from a plantation in Brazil, and so on. That's okay. That this works. And they did estimate basically the fraction remaining on land in time, and I managed to get these data points from them. These are some examples you see to the right there, the graphs. Approximated a two-pool model, a very simple two-pool model, to these data points, and that two-pool model do describe the turnover time. So you see it ranges here, for example, Tunisia, we find like three years, the turnover time, to the US, maybe 61 years, to the United Kingdom, 80 years for a tree harvested in the United Kingdom, not what they actually do with biomass in that country, but it's harvested there. So these are some examples. So then we have both numbers. We have basically the turnover time in the products and the turnover time in the soil. And if your then forestry practice has a positive or a negative effect on the land storage of decaying carbon, is basically just the difference between these two maps. And analysis. And that's what we see in the bottom here. So basically blue means that through forestry and harvest, those countries, the forestry activities in those countries actually increase land carbon storage of decaying carbon. Whereas if you're red, you strongly decrease, or more strongly, the distribution is skewed so that there's much larger numbers on the negative side. You decrease land carbon storage of decaying carbon in red. So most countries, as you can see, the forestry has a negative impact on the turnover time of decaying carbon on land. So that means that we're probably losing carbon from forestry, decaying carbon from forestry. But overall, considering that there's also some rather large forestry countries that are more bluish, the effect is balanced a little bit by them. So another thing that will happen with this is that we will have a warming. So I also wanted to look at basically what happens in the future if we maintain these systems, and we assume that warming, at least in the north, will accelerate soil decomposition. So this map basically shows that there's a significant warming predicted for especially northern countries in the winter, when we also don't have any productivity, but maybe may accelerate soil decomposition. So in this case, it's up to maybe 15 degrees Celsius in the winter months, and then less in the summer months. So that's the colors there. Then basically on the x-axis are monthly values. And when we do this, this figure is basically shows the changes over time. So if we start with the US, in the top left, US harvests the most, according to the databases, the most forestry carbon in the world. And in brackets there, 12% means that in the US, 12% of the global forest harvest occurs in the United States. And the blue shading at year 2000 is basically all these ranges I have by combining various data sets. So that total range there shows the uncertainty in my estimate of soil carbon turnover time in forestry ecosystems in the US in this case. And then I scale this into the future with a number of model predictions of the change in turnover time on the RCP 8.5. It's basically showing that maybe this will shorten. So basically, in the case for the US, where it's also compared to the black line, which is the current turnover time estimate for harvested wood products. The US, if they maintain the same kind of management of forestry products, the same use of forestry products, but the soil carbon turnover rate increases in the future, the difference will actually become larger and larger. So it means that the relative increase in storage through forestry will increase with time. If we look at India instead, it will also shorten, but the current use of biomass or forestry carbon has a rather low turnover time, so the difference is still large. Some other countries, such as Brazil, 7%, are already quite close to their turnover time of products. So the soil turnover time is approximately on the same size as the turnover time of products, especially considering uncertainties, and they are of course larger than what I actually been able to analyze. But still, we can look at some countries like Myanmar, for example, that has like only 5 years of turnover time of the products. The difference will remain very large. Another point I want to make with this is basically we have these then patterns of the soil decaying natural turnover time now and in the future, and it changes, but it may not change that much. And we can also relate these numbers to various things that are discussed as ways to increase land carbon storage. For example, building wooden houses. They have a estimated lifetime of about 70 years, a wooden house, which is not very large or long. And if you compare that to if that wood, for example, come from Brazil, which has a turnover time in the soil of about 15 years, then you would increase the land carbon storage of decaying carbon. If you instead do it in Sweden today, where we have 80 years to start with, we would already decrease. So even using the wood for a wooden house would decrease the land carbon storage of decaying carbon. Now, we may, of course, still offset cement emissions from cement productions and so on, but this is just looking at this carbon. If we do bioenergy and we use Swedish, for example, forestry biomass for that, it will be a large loss in turnover time of decaying carbon. If we use instead tropical forest biomass, such as from Brazil, the decrease in turnover time is maybe only, you can divide it by 5 or so. So it's much smaller. So the difference between the black and the blue line will be much smaller, and the losses of decaying carbon will be much smaller in Brazil. So that's basically some of the results from this, but it's rather simple analysis anyways. So some uncertainties here are waste to energy. So this study assumes landfills. So some of the long turnover times of products are landfills, whereas other countries, especially Sweden, where I know that we basically don't put much in landfills. We burn. We even have a net import of waste to use in our energy production system. So there the black value of 60 is probably not entirely true, but that's for later. This is sort of a first kind of estimate. So another thing, my last thing here to address this. So basically, I started with showing these various pools and land use impacts, if we lost or not, and then I sort of gave up on that global and total experiment where I tried to include everything, and I zeroed in a little bit on decaying carbon, where I can at least look at turnover time, so at least try to estimate them. And another thing I've been thinking about is, instead of doing these model experiments the way I did with the simple model and the way that many other models does it, would be to sort of look at ecosystems that have not experienced much land use through time or much use at all, and then compare the amount of carbon and the productivity and so on in those forests to the surrounding ecosystems, and from that potentially coming up with some kind of estimate of how much carbon has been lost. So if I can sort of account for the differences in the ecosystems and so on, maybe I could sort of map out these, in this case, old growth forests in Sweden across the whole country, and map out how much carbon would be in them, and then compare that to the amount of carbon that's in the managed ecosystems right now. And I could, in that way, come up with some kind of number about the losses in land use, and also the processes in these old growth forests and how they differ. So this is something that in the long run, I would like to do this globally. And we started. Geerte de Jong was a master thesis student visiting from Holland in Lund. And she digitized this map from the 80s. That was only available, it's a report series, I should say, containing 390 mapped old growth forests that was done by the government early 1980s, never digitized, only available in this book form. So she digitized them to this map you can see. So the red dots and the red polygons are old growth forests in Sweden. And in Europe in general, I don't know how familiar you are, but there's very little old growth forest and sort of more pristine ecosystems. Sweden has a larger share of them. Romania used to have also quite large, up until very recently. I still think they have quite a lot, and there's some in Poland and Russia. But other than that, it's not so much left. And some of these ones, so there's Lund is actually in the very south there. It's sort of one of the southernmost points. It's just outside Lund. So in that case, it was a small patch used as a hunting reserve for the nobility. Other ecosystems here, you could assume that they were very hard to get to and use. It could be a mountain top, it could be an island with not much around, or up in the mountains that you see, sort of up in the Scandinavian mountains, we have larger areas. There we have however had quite a lot of reindeer grazing. That's half human management, I would say. But still, this is what we have, and we map them. And also Anthropogenic, a PhD student in Lund, has been working on some of this. So what we did, I will show you the results, the preliminary first results of this from the old growth forest, is we have these polygons, and we basically compare in a paired analysis. As you can see, sort of the illustration on the left-hand side is an old growth forest in red, and then we have a buffer zone around it, and we have data points in production forests around it, which are these kind of purple data points. And we basically average in various ways what's in the buffer around the old growth forests and what's in the old growth forest. And why we do this in a paired way is because it's still shown to be quite difficult to account for the differences in sort of environment. So if for example, this red polygon is a mountain or a wetland and so on, it's still hard. It should probably have lower productivity, lower carbon storage, at least in above ground carbon, not in below ground wetland, but still some differences. And they've been rather hard to address statistically. So we basically have chosen to use this more simple comparison of what we have in the buffer to what we have in the original old growth forest polygon, the red one. In this case, we started this by looking at remote sensing indices of productivity, which you see in these scatter plots. And the scatter plots from A to D is basically just percentiles of the annual distribution. So they don't really show different things. So we can look at either one of them. So in A, panel A, for example, you see that most points are sort of above the 1-to-1 line, where we have production forest. So and a higher number there means that probably it should be related to photosynthesis in some way, not directly, but in some way. And on the x-axis, we have the old growth forest values for these 390 forests. So there's 390 points in this figure. But right, so the mean here, if we just look at the center of this cloud, or we find that the production forest has slightly higher photosynthesis. compared to the old growth forest. But if we trace this line, this regression line, and then the outliers, the highest numbers and sort of a tail of higher numbers are in the old growth forest. So it sort of suggests that the peak numbers of productivity in Sweden are not found in production forests, which is surprising to me, where they fertilize and control for many things and plant these genotypes that should be perfect in agreement with climate change and so on. But we actually find it in old growth forests. And one could also think that perhaps these lower productivity old growth forests, in comparison, they are on lands that are not the best, for example, up in the mountains, in a wetland, or some other things that cause them to be preserved and actually be old growth forests. So be managed in some way. It's rather tricky to find out what the impact is on the old growth forests. I think I have just one more slide here to go. So I will just show you one more. So we also have this national inventory of forests. It's 26,000 sites that have been they've been revisited since the 70s, I think. There's other points dating back to 1920. So they every 5 years or so they go back to and measure all kinds of stuff in these. Unfortunately, quite few of them happen to be in old growth forests, but there's only around 40 or so that's in old growth forests, or 40 old growth forests have any data at all in this inventory. What I just want to show you is here we look at the sort of the scatter plot in the center. Here is the increment, the wood increment of the stems, which I would assume that's what basically in forestry they manage for. They don't manage for photosynthesis, they manage for very good timber. So most of Swedish forestry is sold as timber for construction. So basically, although they are managed heavily for that, we still find that the highest numbers of stem increment are also found in the old growth forest, and they are almost more than 3 times as high as that we can find in a production forest surrounding this old growth forest. And that's surprising. And this is still preliminary, and our plan is to start this summer and go and sample more of this forest to understand it. We also want to expand this. We have a map of old growth forest in eastern Russia. I know there are maps from the US, so I'm basically showing this because this is if somebody else would be interested in doing this kind of work in the US. I'm sort of looking for partners that know forestry, know the data sets, and where we could start building up a more global database of old growth forests polygons, and also data inside and outside of the polygons with management information about management too, so that we can sort of try to simulate this in a model that do account for land use and see if we maybe it can help. I'm still not sure if this data is too noisy to help, but maybe. So these are our findings then from the old growth forest, basically showing that the mean productivity is higher in production forest, but the highest numbers are found in old growth forest, which sort of suggests that land use even forestry that's well managed, do potentially decrease even productivity. Our next step is to look at carbon storage in vegetation, and hopefully in the future also in the soil, which I think is perhaps the most interesting, but also the hardest thing to do. Okay, thank you very much.
Okay, great. Thank you so much, Anders. This was really interesting. I'm going to stop the recording now, and then we can open it up for questions.